This video is on optimization. So optimization is the process of finding the maximum or minimum value of a function. The solution is often referred to as the optimal solution. So we've got three examples to do. The first one, the profit in P million dollars that a company makes if it spends a portion of its income on advertising is modeled by P equals 2 multiplied by F squared times by 1 minus F. Find the portion the company should spend to maximize a profit. So with a question like this, if you are just given a function and you are asked to maximize the profit, all you need to do is find the maximum of the function. So you just graph the function, find the maximum, and there's your solution. So if you were to do that, when you graphed it, you would find it would look something like this. And now we just need to find this maximum point here. So on your calculator, just search for the maximum in the Analyze Graph section, and you will find that the maximum is at 0.667 and 0.296. So 0.667 is the same as 2/3 realistically. You can just say 0.667. Therefore, the company should spend 2/3 of its income on advertising. And that would work out the maximum profit if they did it that way. So with a question like that, often you don't actually need to do the calculus aspect of it. And with an equation like that, you could expand it and do the derivative and work it out from there. But if you are able to use your calculator, just do it that way. So example 2, find the maximum volume of a square-based cuboid with a surface area of 600 centimeters squared. So first of all, let's just draw a quick diagram of a cuboid. So a cuboid is the same as a rectangular prism, except it's the space is a square. So in this one, we know this will be x, that will be x, and then we have something for the height. Now I want to find the maximum volume. All right, so we know we're going to need our volume equation. So the volume of this would be the area of the base, which is x squared multiplied times the height, because it is just a prism. And we've also been told the surface area, which means we're going to need to use a surface area formula too. So with this type of idea of optimization, often you will be given or have information to create two separate formulas. So our surface area of this, we're going to have 2 of the base, because you've got the base and the top of the shape, which would be 2x squared, because you've got 2 of those. And then you've got the outside sides are all the same too. So you're going to have 4 of those, so it would be plus 4 times xh. And one thing we also know about here is the surface area is 600, so we know that this equals 600. So 600 equals 2x squared plus 4xh. So now we've got 2 formulas, one for volume and one for the surface area. Now because we're wanting to find the maximum volume, we need to keep that equation, so the v equals x squared times h, and we need to do some manipulation of the surface area and sub that in. The reason we want to do that is because we don't want 2 variables. We don't want an x and a h, we just want 1. So what I'm going to do is rearrange the surface area formula, so it's h equals, and then we can sub that into the volume formula and solve from there. So first of all, I'm going to divide everything by 2, because to make the numbers a little bit nicer. So we'll end up with 300 equals x squared plus 2xh, and then we're just going to rearrange. Now we've got that, we can sub that h value into our volume formula. So our volume formula would then be x squared and multiplied what we have for h, which is 300 minus x squared over 2x. Then from there we can just simplify all that down. So we're going to expand the bracket, so that will be 300x squared minus x4 all over 2x. We can simplify that once more. We don't need to, but if we are going to do the derivative etc. by hand, then you would need to simplify this again. Divide both sides by 2x, so we'd have 150x minus a half x cubed. So now we've got an expression for the volume. We need to optimize this to find the maximum. So if we want to do this by hand, first of all, we need to find the derivative. So v dash would equal 150 minus 3 over 2x squared. And then we want to make that equal 0 to find where our possible maximums are. And then if you were to solve this, you would find that x equaled 10. So our maximum is then when x equals 10. And then from there, we can sub 10 into our volume formula to then find out what the maximum of volume is. So we know that x equals 10, and we can put that into the volume. So the volume would equal 150 times by 10 minus a half times by 10 cubed. And if you work that out, you will find that the maximum volume is 1000. Now to do this with your calculator, once you'd actually got to the step with a volume equation, so even this step here that I've just started, you will be able to graph that in your calculator and then find the maximum of the curve from there. But obviously we do also need to know how to do it by hand, just in case we are required to do that in our exam. Okay, next example, example 3. We've got this lovely diagram here, and we want to show that if the area of the rectangle is A, then A squared equals 400x squared minus 4x to the power of 4. Now what I'm going to do is I'm going to create a nice little right angle triangle here from the edge, from the corner of the rectangle, the edge of the semicircle to the middle. Now, one thing we do know about this though is that this is 10. And that is because that is the radius of the semicircle. We know the diameter of the semicircle is 20 centimetres, which means the radius has to be 10. So we actually know that diagonal there. So from that, we can then find an expression for the half of the base of the rectangle using Pythag, and let's just call that y. So we know that 10 squared would equal x squared plus y squared. Y squared would equal 100 minus x squared. And then y would equal the square root of 100 minus x squared. So we now have an expression for half of the base, which means our area of our rectangle is going to be the height, which is x, multiplied by the base, which would be 2 times the y, because y is only half the rectangle. So it would be 2 times the square root of 100 minus x squared. Now we want a squared, which means we need to square all of this. And if we do, we'll get a squared equals x squared multiplied by 2 squared, which is multiplied by the square root of 100 minus x squared. And square that one. If we do that, we'll end up with x squared times 2 squared, which is 4x squared. And then the square root just cancels there, and we end up with 100 minus x squared, and then we can expand the bracket, so we'll end up with 400x squared minus 4x to the power of 4. Part B, find d dx of a squared, and hence find the value of x that maximises a squared. So we want to find the derivative of a squared first, and then we want to maximise it. So let's find the derivative of a squared. So the derivative of a squared would equal 800x minus 16x cubed. And we have to find the value of x that maximises. So to maximise it, remember, we need to make the derivative equal 0 to find our maximum. And when you solve this, you will find that x can equal 0, or x could equal the plus or minus of root 50. Once again, you can just do that in your calculators. If you do it on your GDCs, you will obviously get a decimal answer rather than square root of 50, and that is fine. Now we need to know where the maximum is. Now we've got to think logically about this situation. X is a length, and we know it's a rectangle. So we know that x can't be 0 because we can't have the length of 0. And we also know length can't be negative, which means our only option for the maximum will be at x equals the square root of 50. Now double check this in your calculator so you can just graph that original function of the 400x squared minus 4x to the power of 4, and just double check that that maximum point is at the square root of 50. And if you did that, you would find it would be. Then C, find the dimension of the largest rectangle that can be inscribed in the semicircle. So we know that x is the square root of 50. From here we can find out what y is, which would be y equals 100 minus the square root of 50 squared, which just equals the square root of 50. And obviously we need to multiply that by 2 to give us the full length of the rectangle. The dimensions of the rectangle will be the height being square root of 50 and the base being 2 square root of 50. And that's optimization.